Something just entered our solar system, and it's not staying. It's not looping like a planet. It's not falling in like a normal comet. It's slicing through, fast, on a path that doesn't close. And when astronomers ran the numbers, the math didn't point to the sun. It pointed outward. Because this object isn't bound to us. It has excess speed, energy to spare, which means one thing. It didn't start here.
You clicked for a mystery in our own backyard. Good call. An object is cutting through our solar system on a path that doesn't loop back like our planets or most comets. In this video, we'll break down why a hyperbolic trajectory matters and what its unusual speed tells us. We'll compare its light curve against familiar comets, look at the lack of a classic tail, and dig into hints of non-gravitational acceleration. By the end, you'll know why some scientists consider exotic possibilities, from exotic ices to engineered sails, and what the Vera C, Rubin Observatory is poised to reveal next. You saw the path. Now here's why that single curve rewrites where it came from. In our solar system, most travelers are bound to the sun on closed loops. Planets and many comets trace ellipses, squash circles that always bring them back. Visitors don't loop. They follow open paths. A hyperbola is a one-and-done flyby, in, around, and gone. The key difference rests in energy. If the total energy is negative, you get an ellipse. If it's positive, you get a hyperbola. That positive energy shows up as excess velocity, v infinity. Think of v infinity as the speed it would still have far from the sun after all the gravitational pulling is done. If v infinity is not zero, it didn't start here. So why would an object arrive on a route that never closes? Because it wasn't born inside the sun's nursery. Interstellar space holds debris ejected from other star systems during their chaotic youth, and some of those pieces wander into our neighborhood. The fingerprint is in the numbers. Eccentricity measures how stretched an orbit is. For an ellipse, it's less than 1. For a hyperbola, it's greater than 1. When the fit yields e greater than 1 and the inbound speed stays high even far from the sun, the math says visitor. Use an airport to anchor this. Local planes circle, line up, and land. Their speeds and approach angles follow the airport's playbook. Now imagine a long-haul jet slicing across the airfield at cruise speed without extending the gear. It's not landing. It's transiting. That's the hyperbolic case. The velocity and trajectory tell you it didn't originate in local traffic. Let's put numbers to it. Long-period comets fall inward from the distant Oort cloud, and by the time they reach the inner solar system, they tend to move near solar escape speed. But their v infinity is close to zero because they're still bound. Known interstellar objects buck that pattern. One well-studied visitor approached at about 26 kilometers per second relative to the sun. Another cleared roughly 32 kilometers per second on entry. Those speeds are tough to reconcile with formation inside our system because the protoplanetary disk and planetary dynamics don't leave you with that much excess energy. If you try to jam those data into a stretched ellipse, the fit breaks. How do we even catch these? Surveys like Pan-STARRS scan the sky, taking repeated images and looking for dots that move against the star field. Fast movers pop out through algorithms that compare positions over minutes and hours. Once you have a handful of positions, orbital software tests thousands of possible paths. If every bound solution leaves systematic leftovers, tiny offsets between the predicted and measured positions, while the hyperbolic solution wipes those residuals down to the noise level, you accept the hyperbola. Small astrometric residuals across several nights and from different telescopes carry a lot of weight. Even with a short observation arc, a clean, consistent track pins down the orbital class. You don't need months if the data are precise and the motion is unambiguous. That's why this trajectory matters. A hyperbolic fit with a real v infinity means we're not watching a homegrown comet that got stretched. We're seeing an object that cruised in from between the stars, swept past the sun, and will fade back into the dark with speed to spare. The path answers origin before we touch composition. And that sets up the next question. If the orbit says visitor, then we turn to the body itself. Does it throw off gas like a standard comet, or does it stay quiet like a rock? The next clue comes from its behavior under sunlight, how it brightens, how it spins, and whether gravity alone can explain its motion. So the orbit screams visitor. Now look at the body's behavior. If it's moving like a comet, where's the glow? Comets brighten because sunlight heats their surface, turns ices straight to gas, and drags fine dust along for the ride. That evaporated gas forms a fuzzy coma and a tail. It also gives the nucleus a tiny push. Orbit calculators include that push with a standard recipe called the Marsden parameters, which track how the acceleration changes as the comet gets closer to or farther from the sun. You expect a pattern tied to sunlight, stronger near perihelion, weaker as it recedes. Here's the twist. The motion isn't purely gravitational. You can measure a steady, extra acceleration, but deep images show no classic dust coma. Surveys that first spotted it and follow-up telescopes looked for a tail and didn't find one above their detection limits. At the same time, its brightness doesn't stay steady. It swings up and down, which often means an elongated shape tumbling and showing more or less surface area as it rotates, or a patchy skin with bright and dark regions turning into view. To see how odd that is, compare it to well-behaved comets. Halley's Comet pours out gas and dust. Spectroscopy catches clear bands from common molecules when it gets warm. The second known interstellar visitor, 2I/Borisov, behaved like the textbook case 2. Clear detections of gaseous species and a visible tail. This new object doesn't match that profile. No strong dust signature. No obvious lines from common volatiles in the spectra taken while it was bright enough to study. Yet the orbital fit still demands a gentle, smooth push away from the sun. That push scales with sunlight. If the effect comes from outgassing driven by heating, the magnitude roughly follows 1 over the square of the distance from the sun radiation pressure. The force of light itself also drops with that same pattern. The measured trend sits in that family, stronger closer in, fading farther out. So you can build 2 broad classes of explanations. Either it's venting something that doesn't kick up much dust, or it's so light for its size that sunlight gives it a measurable nudge. Now the hypotheses. One says it carries exotic ices, such as molecular nitrogen, that can sublimate cleanly without dragging much dust, leaving a faint or undetectable coma. Another suggests a shard chipped off the surface of an exopluto, basically a nitrogen-rich crust fragment fractured by impacts and ejected into interstellar space. A third goes geometric. Make the object extremely thin, with a large area compared to its mass, and radiation pressure alone can account for the acceleration without vents. Each comes with trade-offs. A nitrogen iceberg erodes rapidly under sunlight, so you have to explain how a chunk large enough to detect survived the trip through interstellar space and still had enough material left when we found it. The ultra-thin option leans on a very low density and a high area-to-mass ratio that works mathematically but pushes you toward materials and structures that are rare in nature. Meanwhile, a conventional comet with unusually low dust content could hide its gas emissions below the detection limits of the instruments used, yet still provide a steady thrust. The light curve complicates it further. A highly elongated body can create large brightness swings, but strong outgassing should introduce torques that alter the rotation in telltale ways, and those signatures aren't obvious. So why no tail, and what's the mysterious push? The orbit demands a non-gravitational acceleration consistent with sunlight-driven physics. The missing dust points to unusual composition or structure. If this mix, silent spectra with a measurable shove, is common among visitors, the next wide-field surveys will catch many more and give us the statistics to separate nitrogen shards from thin sheets. Rubin's nightly cadence will flag the fast movers quickly, and the early spectra will tell us whether we're seeing clean ices, low-dust vents, or sunlight doing more work than we expected. One strange traveler can reset our expectations: a confirmed hyperbolic path, a quiet spectrum, and a steady non-gravitational nudge point to a class of debris we haven't cataloged here. That means composition, shapes, and surface physics that don't match our usual comet playbook. Watch what the Vera C, Rubin Observatory turns up. Its rapid, deep sky sweeps will catch more fast movers early, feed orbit fits fast, and deliver spectra while they're bright. With a larger sample, we can test nitrogen shards against thin sails using real statistics, not guesses. When the next one streaks in, will it grow a tail or slip away in silence?
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.